Welcome to the Introduction to Landscape Ecology with R workshop. This material was created by Jakub Nowosad and Maximilian Hesselbard for the YALI North America 2020 annual meeting. You can find links to the slides and the code and other materials in the description below the video. The workshop was split into two parts. This video is about the first part of the workshop. First part is about introduction to spatial data analysis in R. And I need to start with showing you two main representations of spatial data that exist and how are they implemented in R. So we have, if we think about spatial data, we have two main representations. And the first one is called raster data. And raster data is usually, or the simplest form of raster data is described as a matrix with values. So we have two dimensions. So we got columns and rows. And each of those cells, or we call them grid cells, contains a value. For example, first cell contains value of 22. And next, if we look at this data, it's usually a colored map, which basically means that those values in cells are connected to some colors. And this way we can see how those values, are they low, like red values, or high as green values. In raster data, we can also have something which is called NA, not available. So this is a representation of missing values. And in our map, this is represented by white color. And there are several packages in R that try to represent raster data, but still the most popular is called a raster package. So to read data using the raster package, you just need to use a function called raster and provide a file path to your data set. So in this code, I just use raster function and read data called example_elevation.tif. And this way we've got a new object called lfdata. And this new object is a class called raster layer. It has 550 rows and more than 700 columns, which makes almost 500,000 of cells in total. Here we also see resolution of this data, which is 0.003 in one dimension, 0.002 in second dimension. We have a value of extent. Extent is borders, it's a coordinates of the borders of our area. We have something which is called CRS. We'll go back to this concept at the end of this part of the workshop. We have a source, which is a total complete file path to our file on our hard drive. And we have values. So this example elevation has values starting from 57 up to almost 180. And if you want to learn more about this package, you can either open the help file of this package or click on the links that we provided on the slide. The second main representation of spatial data is vector data. And vector data is slightly different because with rasters, we've got a matrix with values. So we've got a continuous values. However, in the vector data, vector data is mostly built upon points. And if you have just one point, it's just a point. If you have many points, it's a multi-point. If you connect those points by line, we have a line string. And if we have the first and the last point in the same location, we have a polygon. So we can represent area using this polygon. And in R, the main package used for vector data right now is called the SF package. which stands for simple features. This is a name of a standard used for that in that package. And to read vector objects in R, you need to use read_sf function and provide path to your file. This way we can read this new object called study area, and you can see that this object is a type of polygon. So you can see here on the left this interactive map, and this is our polygon. So we have a borders, and I made this map without any fill inside, but it's basically a polygon. So everything here is part of our polygon, and everything here outside of the polygon is not a polygon. We also have a bbox, which basically is the same as extend in the raster package. We have here we've got approach for string, but it's the same as coordinate reference system. And we have some table, and it could be a large table. In this case, we only have a one column called ID. And again, you have several links on this slide. You can go and learn about this representation and this package more. So you know that already, but I'm going to show you that together. During this part of the workshop, we are going to focus on those two packages. So if you want to follow the workshop, you need to first attach those packages using library SF and library raster. And next you need to read those two files using read_sf and raster and provide the file path. If you are using the project that we provided, it should work without any problems. And now we can try to create our first map. So if I read those two data sets, so the first one is just a polygon, and the second one is a land cover data. And we can plot them quite quickly in R. So we can just use a function called plot. I need to provide the input data, so our raster data first. So this green, yellow, and reddish data. I'm also specifying axis equals to true to get coordinates. So this frame around our area. And next, I want to add all the geometry of our study area. And I want to have it in the same map, so I need to specify hat equals true. And probably it's not that easy to see, but there is a black border in the middle of our area. So that's our study area that we are going to focus on during this workshop. So this is all about spatial data representation. But one of the probably most important concepts related to spatial data is how to make a map. And R is great to make a map using programming language. And one of the best packages for that purpose is a package called Tmap. And this package is very versatile because you can create static maps, animated maps, and interactive maps using just this one package. And if you go to the package website, you can find a lot of additional materials. For example, you can find all of the code on how to create those examples that you can see on the slide. So all of those examples were created using this package. And for most of them, it's just a few or maybe a dozen lines of code. So how Tmap works? So basically, maybe some of you are already familiar with the ggplot2 package. So both those packages, Tmap and ggplot2, share the same idea about some grammar of graphics. And there are slight differences, but the main idea is very similar. So with Tmap, the main function of the Tmap package is tm underscore shape. And you will see that most of functions in the Tmap package starts either with tm underscore or tmap underscore. So tm underscore shape specifies our input data. So for example, we want to create a map of our study area. However, tm underscore shape doesn't work alone. So if you just type tm shape study area, you'll get an error. No layer elements defined after tm shape. What does it mean? Basically, we need to specify how we want this data to be visualized. Because if you have, for example, polygon, it could be visualized as an area with some borders, or it could be visualized just by the borders, and we need to specify that. And for example, using Tmap, we can use another function called tm borders to specify how this data should be represented. And you can see that we need to connect all of the elements in the Tmap package using the plus sign. So here I created this simple map, so we can see that we've got the borders of our area. We also have frame, our map frame. And this was done only using these two lines of code. First one, specifying our data set, plus specifying how this data set should be represented. And using this fashion, we can add more and more layers, add more and more elements to our map. So for example, most of the times already, actually, maps contain some additional elements like scale bars or north arrows. And we can add those elements with plus and another functions from the Tmap package. So for example, tm underscore scale underscore bar create this scale bar you can see in the right bottom corner of the map. And tm underscore compass gives us this north arrow here. And each of the map elements have a lot of arguments that we can specify. And the most basic argument is the position argument, which expects two elements, vector with two elements. So here we specify this vector for scale bar with position equals to c. So we are creating vector right and bottom. And that's why we have this scale bar here. And we put a compass in left top. That's why we have it here. So basically, position needs to be specified with the first argument, which is left, center, right. And the second argument, which is bottom, center, top. You can also use numbers from 0 to 1 to specify positions of your map elements. Next part, again, many maps contains that. It's a map title. And to create a map title in Tmap, we are using a function called tm layout. So this function is related to our overall map. So it gives us a lot of options, like you saw already during the exercises, when we changed also the background using this function. So here I specified my main.title to study area, and that's why I got this text here. So this is a very simple map, but we can already try to use this map using two versions of the Tmap package. So I already told you that many functions in Tmap package starts with tm underscore, and those tm underscore functions, they are used for map elements. But Tmap package also has function that starts with tmap underscore. And what's the difference? The difference is that tmap underscore, those functions are about all elements except our maps. So we are not creating our maps with these functions. They are doing something different. So let's try this code. Maybe I can move to my R session. And so what's going on here? So basically, Tmap allows to use the same code for static and interactive maps. So I'm going to comment out this to group of code. So you remember that if I just use this code, I have this very, very simple map. But using tmap mode with the argument view, I'm changing the mode from static to interactive. And right now, if I put it and run the same code again, I have an interactive map. And that's very useful because the same code, or more or less the same code, you can use in those two modes. So right now I can zoom in, zoom out, pan, and click on my objects. I can change the background of my map. You can see that we are right now west from the Augusta city in the Georgia state of US, and so on. So we can turn off this polygon, etc. So that's very powerful. That's one of the main advantages of using Tmap for making maps. And if we type and run again tmap mode, but this time with the plot argument, we are going back to the static map mode, and we are creating the static map once more. So I'm not going to show you that again during this session, but you can try those two map modes by yourself today during the practicals. Okay, so you probably, if you are working with ecological data, often ecological data is in form of raster data. So this time we are starting the same with TM shape, but this time our object here is a raster. So LC data is a raster object. And if you try to do TM shape plus TM borders, you will get an error because you cannot represent raster data as borders that easily. However, you can use TM underscore raster for that. And you can see that we got a raster map with all of our colors and legend, which is not that visible yet, but we could change the background, or we can move this legend somewhere else and see it clearly. So we can do that. So as I told you before, those overall options are specified in TM underscore layout. So there we are not only changing the background or putting a map title, but this is also the place to move our legend. And I decided to move the legend outside. So there is an argument called legend.outside. And if we change this argument to true, our map legend is automatically moved to the right of our map. And now you can see that each color in our map represent different land cover category. However, by default, we've got a lot of land cover categories that exist in the whole data set, but maybe not in this specific area. So I decided to just show me those land cover categories that are in this raster. So I use drop.levels to true. So right now I have less elements here. And also previously, we've got a legend title which wasn't that informative. It was a name of our layer, example _ landscape. So probably it's better to change that to some more informative title with the title argument. So instead of Tm_raster, I change my title to land cover. And right now, our map makes more sense and it's more visible. And now we can connect those two maps together. So we can connect the map we created before with our study area with this raster map. So basically, we are starting from the first layer. So what is our bottom layer? And usually it's the raster data set here. And next we are connecting that with the plus sign with all of the rest of our map elements. So we are putting our borders. They are not that visible, but I can see them that they are here and here. We are also adding our scale bar here and north arrow here and our map title here. We can make these borders more visible with some small changes to the default arguments. Because by default, the border color is set to gray. And I maybe want to change that to a different color. So I just need to specify col equals to, for example, black. And if I want to make the line more thin, I can just change the LWD argument to larger number. I think by default it's 1. So if we change that to a larger number like 3, we got a more visible line. So this is how we can distinguish this line from the raster data in the background. So that was an example of categorical rasters. So land cover data has categories like previously we've seen, but often we also work with rasters that are called continuous rasters. So in continuous rasters, each value, each cell could have a totally different value, and those values are not related to any categories. And one of the probably most often used examples is related to elevation data sets. So we also provided you with one of this kind of data sets. So you have a file called example elevation.tif. And if we do very similar code as before, so just tm shape, our name of our data set, plus tm raster, we have a simple map of this area. But of course, this map is not perfect. We need maybe to do some tiny adjustments to improve this map. So what can we do? So one thing that I usually do when I'm plotting continuous data, I change the style of my raster. So if I put style equals to cont from continuous, you can see that right now my legend and my colors, they change gradually. They are not previously they were, we had 7 different categories of elevation. Right now, we don't have categories. Our values and colors change smoothly from one value to the other. And the darker the value, the higher the elevation is on our map. We can again, in the similar fashion as before, change the legend title, and we can move our legend outside of our map using legend.outside equals to true. We can also, as you already done that in the first practical part, change the color palette. And to change the color palette, we need to provide the shortcut name of this color palette. I use a color palette called RDYLGN, which stands from red, yellow, green. So you can see red, yellow, green. However, I started with minus. And that's really important because this means that this color palette will be in reverse order. So instead of red, starting from red, we are starting from green. And without that minus, we will have the flipped version of this color palette here. And if you want to learn more about possible color palettes here, you can run this line of code. So there is a function called Palette Explorer. It's an interactive application with all of the possible color palettes that you can use. And there are several dozen of those color palettes that are recommended to use. But here you can also provide your own color palettes using the hex values. So you can just provide a vector of hex color values here. Okay, so let's say that we are happy. That's a good map. We just want to save this map. So saving a map using the Tmap package requires two steps. The first step is to create a new object. So the same as we read some data sets, we are creating new objects using the arrow sign or the equal sign. And we have a new object called map1. And next, we can save this map using tmap_save. And again, tmap, which stands for functions outside of making maps. They are functions to do something else. And in tmap save, saves our map to a file on our hard drive. So for example, if we just provide map1 and my first map.png, we'll have a static map in the PNG format. However, if we type map and my first map.html, we will save this map in the interactive version, interactive form. So you can open this map using your, for example, web browser. All right, so this is all of the things I want to show you about introduction to the Tmap package. This package is very powerful. There are many more possibilities, but don't worry, at the end of this part, I will also provide you some links and information to the additional materials that you can learn more about it. However, R is not only about making maps. You can do much more with spatial data in R. And this is just a summary here that we can do some attribute operations, we can do some topological operations and focal operations. And due to the short time of this workshop, we are going to focus on two very useful elements. So I will show you a little bit about vector raster interactions and also about reprojecting spatial data. So what's about vector raster interactions? So we have those two types of data, vector and raster, and they can interact with each other. So you remember that we've got this land cover data which is in shape of rectangle, but our study area is a little bit smaller and it's not regular. So if we just want to cut to the borders of our data set, we need to use the crop function from the raster package. And using crop function, we don't have this data from the west side or data from the east side. We are just focusing on the data around our study area. But you need to remember that the crop function just creates again the rectangle view of our data, but it's fairly fast. And if we want to have just exactly the data inside of our study area, we need to use the mask function. And it's usually done in two steps. We need to first crop our data, and next we need to mask our data. So the output of the crop function is here. This is our polygon data set. And we created a new data set called ALC data masked, which is exactly this raster data set here. So this is how you can just focus on your study area, not on the entire data set you downloaded from some website. Second, very important topic that I think that everyone should have at least some knowledge about is about spatial coordinates. And it's very important when you do some spatial analysis and when you are applying some spatial methods for landscape ecology to know about them. Because most global data sets, but not only global data sets, comes in geographic coordinates. So our data sets are described by two values, one of longitude, so it could be east or west, and one of latitude, like south and north. And this type of coordinates, it's specified a location on an ellipsoid, so on a sphere. However, we are not working on a sphere usually. And most of the methods we are using in landscape ecology, they work on a flat surface. And they usually prefer those two-dimensional view of the world. And we've got, for that purpose, we've got projected coordinates. So projected coordinates, they are described in some units of distance, like meters or feet or something similar. And so we have two axes, and the values are changing in those axes. And in R, right now we are in the middle of changes in this, but in R we are using some techniques to describe those coordinates using a concept called coordinate reference systems, which basically means that we can have many different ways to represent the same data, but using different coordinate reference systems. Why is that? Because everyone wants to have its data as much correct as possible. And because of that, there are many different ways to put the data on the map. So each country creates their own coordinate reference systems. There are also changes with time. Also, like US states have their own coordinate reference systems, and so on and so on. And there are many of those coordinate reference systems that exist in the world. And if we look at the vector data set, or with our vector data set called study area, we can use function called st_crs to see its coordinate reference system. And you can see that we've got this fairly long description, which is probably hard to read, but there are few things that probably you can understand. One is that our unit is meter, which means that both our axes are in meters. So if you are moving in our map, we are moving in meters. And second fairly important thing is that our projection is equal area, which means that objects on our map will have preserved area, and this area will be fairly correct. For raster data, there's a different function called CRS. And we have a different representation here. But again, you can see that units also equals to meters. And that's basically the same projection. So often when we work on some projects, you have data sets, and those data sets could have different projections. So let's say that we have two data sets and they have different projections. So we need to move all of our data sets to one projection. And I already mentioned those two approaches with coordinates. So we have geographic coordinates, and because of that, we also have geographic coordinate reference systems. And we have projected coordinates, and related to them, projected coordinate reference systems. So geographic coordinates, most of the time we are using, at least now, coordinate reference system called WGS84, which has a code 4326. However, I think this is the good way to integrate your data. It's a good way to map your data, but it's not proper way for most of spatial data analysis. For spatial data analysis, most of the time you work on a local area or regional area, and you should transfer your data to projection of this local area. And gladly, often there is some CRS, so coordinate reference system for this area. And you can find them using this website here. And just to show you that fairly quick, there is a function called sctransform, and this function is for vector data. So for example, we can get our vector data and extract CRS from a different data set, and using that, we can convert two data sets in the same projection. Or we can use raster data information and do the same. Or we can provide some number, which is called EPSG code, or we can provide another different code. And you can find all of those codes on this website, or you can just click on this link. There is a chapter in the Geocomputation with R book about the projections. For raster data, we have a function called project raster, where we are providing raster data and some representation of projection, or our vector data and its representation of projection. However, for raster data, there is one important additional thing, which is that method, there's an argument called method, and it's very important here. Because if you have categorical data, you should use method called NGB, which stands from neighborhood, so nearest neighbor. And if you have continuous data like elevation data, you should use method equals to bilinear. And just quickly, I'll show you examples here. So our original version of the elevation data looks like this. So both dimensions were described in degrees. And you can see on this map that 0.02 degrees in this dimension is different than 0.02 degrees in this dimension. And that's a problem. However, we can use project raster to move that data into a projection of our land cover data. And right now, we've got our units in meters. So both dimensions are right now in meters. Hour and a half is way too short for to learn it all. That's why I put this slide here, where you can learn about more resources related to spatial data analysis in R. On the bottom, you have some links to the book called Geocomputation with R, which is open source. You can go there online and learn more about spatial data analysis in R. There is also another links to spatial data science with R website, when there are a lot of materials related to the raster package. There is a R-Spatial website with blog posts and also another book in progress with more advanced topics. There is a GIS Stack Exchange website where you can ask your questions related to spatial data analysis in R. And what's also great, if you use Twitter, I encourage you to use hashtag #RSpatial and hashtag #GeoCompR, where you can ask questions or show your work that was done using R packages. If you want to learn more, last month we recorded a video about the recent changes in R Spatial, and some of you got some problems with projections, and those problems are probably mentioned in this video. And if you want to learn more about the whole landscape of data analysis in R, so what we can do in R related to spatial data, there's also a video from last year and slides that you can go and check. There is, again, there are a lot of links, there are a lot of resources. You will find them there.